Monday, we will have exercise. So don't forget to bring your calculator, no, engineers. And I will discuss some problem solving regarding to the topics that we discussed. Ano? So again, don't forget to bring your calculator on
Sir,
Monday.
sir, excuse po.
Yes po.
Hindi po ako natawag ulit sa attendance. Hernandez po.
Wait po. Absent po, Vincent, right?
Opo. Hindi po
Late ka po
natawag.
ba?
Hindi po natawag kanina.
Hindi ka po ba late?
Hindi po. 8:30 po ako sakto nandito.
Sige po.
Thank you po.
And for today, we will have our discussion regarding to temperature measurement, right? So, mabilis lang to. And then use the remaining time for your rest or depende. Kayo nang bahala. Ano? Okay, let's start. And for your midterms, for your midterms, we will have a multiple choice and some problem solving. Ano, engineers. And for our laboratory, it will be conducted in finals. Okay po, engineers?
Yes po. Okay po, sir.
How about others?
Okay po.
Okay. So let's proceed and presenter, go ahead.
Hello, good day everyone. We are here to present our topic about temperature measurement. But first, let me introduce the members of our group. I am Shane Balriseda and I will be discussing the importance of the temperature measurement. Next will be Engineer Hoson who will explain the different temperature scales. And finally, Engineer Kalingasan, Engineer Barola, and Engineer Gida will discuss the different temperature measurement temperature measuring instruments. To begin, temperature measurement is the process of determining how hot or how cold a substance, object, or environment is. This is done using instruments like thermometers, thermocouples, or infrared sensors to quantify the thermal state of a material or system. Next po. So, why is temperature measurement so important? Engineer Aguila, pakibasa nga po. Yun nga, sabi ni Engineer Aguila, temperature measurement plays a crucial role in monitoring, controlling, and understanding thermal conditions. In medicine, for example, measuring body temperature can give us vital health clues. Industrial settings rely on temperature control to ensure product quality and safety, while environmental scientists use temperature data to predict weather changes and study climate patterns. Next slide po. There are different tools and methods used to measure temperature, each suitable for specific applications. Traditional mercury thermometers, for instance, are still used, but we also have more modern options such as digital thermometers and infrared devices. These advanced tools allow for quick and accurate temperature readings. In conclusion, temperature measurement is fundamental in our daily lives and across various industries. With the right tools and accurate readings, we can ensure safety, quality, and efficiency in processes that affect our health, environment, and technology. I'll now pass the floor to Engineer Hoson, who will start by discussing the different temperature scales.
So temperature scales is something that is very familiar with us engineers. Ever since we started our computation subjects, temperature scales or temperature measurements has been present. And we know that temperature is measured in SI and in English units. Next slide po. So for SI units, we have Celsius and Kelvin. So to start, Celsius, it is a widely used globally. It is widely used globally for science and daily life. And water freezes at 0 degrees Celsius and water boils at 100 degrees Celsius. So for our formula, we have degrees Celsius is equal to the quantity of degrees Fahrenheit minus 32 times 5 over 9. So kung mapapansin po natin sa ating module, ang nakalagay po dun ay plus 5 over 9. So mali po yun. Kailangan po ay naka-times. And then for Kelvin, used in scientific context, 0 Kelvin is absolute zero and it has no negative values. So for the formula of Kelvin, it is simple na 273.15 plus the value of degrees Celsius. Next slide po. Now we have our English units. We have Fahrenheit and Rankine. So first, Fahrenheit, used in the United States for weather and cooking. Water freezes at 32 degrees Fahrenheit and boils at 212 degrees Fahrenheit. So for the formula, we have degrees Fahrenheit is equal to 32 plus the quantity 9 over 5 times degrees Celsius. And we have Rankine, used in US engineering fields based on the Fahrenheit scale, and absolute zero is at 0 degrees Rankine. So for the formula, we have 459.69 plus the degree Fahrenheit. So next slide po. So I have here some simple examples of temperature conversions. We have number one, an overheating motor has a temperature of 247.56 degrees Fahrenheit. What is its temperature when expressed in degrees Celsius? Number two, at the end of combustion, temperature is 1037.89 degrees Celsius. Express the given temperature in Kelvin. Number three, the coldest inhabited place on Earth has a recorded temperature of as low as negative 88 degrees Celsius. Suppose the temperature is expressed in degrees Fahrenheit. What is now the temperature reading? And lastly, in our solar system, Venus has a temperature of 867 degrees Fahrenheit. What is its temperature when expressed in Rankine? So I will not call on anyone specifically po. I want everybody to participate and type their answers in the chat box. Bigyan ko po kayo ng konting oras. Hello, hello. So, meron na pong mga nag-send ng answers. Palipat po ng next slide para makita nila kung tama sila o hindi. So, the answer for number 1 is 119.75555. Basta madaming 5. So, tama naman po. Then, for number 2, we have 1311.04 Kelvin, which is again, tama. Ang gagaling. Number 3, we have negative 126.4 degrees Fahrenheit. Again, tama. Grabe, ang gagaling ng O7. Lastly, 1326.69 degrees Rankine, which is again, tama. Grabe, papasa kayo talaga. So, before we proceed to our next discussion, I will pass on the floor to Miss Gladys Maygida for the icebreaker.
For our icebreaker, next slide po. You have to guess what temperature instrument will be presented as an overview of the following instruments that we will be discussing. So first, who wants to answer? Mr. Angeles.
Pressure thermometer po.
That's correct po. Next. Mr. Panopio.
Quartz thermometer po.
That's correct po. Next. Mr. Aguila. That's correct po. And next. Mr. Romero.
Thermocouple po.
Correct po. Next. Miss Manes.
Liquid in glass thermometer po.
Correct po. And that's it for our icebreaker. Thank you to those who participated.
Now moving forward with our presentation, let's discuss about the different temperature measuring instruments, starting with bimetallic thermometer. Next slide po. So bimetallic thermometer, it is a type of temperature measurement device that uses the principle of thermal expansion to measure temperature. It consists of two different metals with different coefficients of thermal expansion bonded together in the form of a strip. When the temperature changes, bending of bimetallic strip occurs and then translated into a temperature reading. So here's the video po of how to use bimetallic thermometer.
Hi, I'm Barrett from Thameson, and today we're going to talk about bimetallic thermometers. First, we'll see how they work, why they are used in the industry, how to select one, and finally, why calibrating them is important. How does a bimetallic thermometer work? A bimetallic thermometer uses a bimetallic strip to measure temperature. The thermometer stem comes in contact with the fluid. Within the stem is a bimetallic strip, which is essentially two strips of different metals bonded together. As temperature changes, the metals expand or contract at different rates, causing the strip to bend. With proper calibration, the bending moves a pointer on the dial to indicate the temperature changes. Bimetallic thermometers are common for industrial applications because they are simple, robust, and provide accurate temperature readings. They are easy to install and maintain, and ambient pressure temperatures don't affect the reading. They also have a good cost to performance ratio. Bimetallic thermometers are not suitable for extreme temperatures and are typically used between -70 and 600 degrees Celsius. They also have a slower response time compared to other industrial thermometers, such as a gas expansion thermometer. To select the right bimetallic thermometer, consider these 5 main selection criteria. First, the temperature range. Ensure the bimetallic thermometer is rated for the temperature of your application. Second, the stem length and orientation. Determine the immersion length or depth of the tank or pipe where the thermometer will be used. Use this to determine the stem length. Next, decide if you want the stem to be oriented in the rear or under the cabinet. This ensures that once it is installed, you can easily read the dial in the cabinet. Third, cabinet material and diameter. Ensure that the cabinet material is suitable for the environment and small enough to fit inside your application, but big enough to properly read. Fourth, know how accurate of temperature readings you need for your application and select the appropriate accuracy class for your thermometer. A thermal well is used to protect the stem from the fluid and allows for easy removal of the thermometer. Calibrating your thermometer is essential. A thermometer typically needs calibration if it's new and it lacks calibration certificate, has been in storage for an extended period, or if you suspect inaccurate readings due to handling or dropping it. Always calibrate to a temperature close to the process media temperature. Calibrate it manually with the ice point or boiling water method, or send it out for calibration. If you would like more information on bimetallic thermometers,
So we have liquid in-glass thermometer. It is one of the most common temperature measuring devices. Both the liquid and glass expand on heating, and their differential expansion is used to indicate the temperature. Its precision depends on the care used in calibration, wherein it should be occasionally checked against the ice point to take into account the aging effects. Here's a video po about liquid in-glass thermometer.
We will deal with the design and operation of a liquid in-glass thermometer. So let's get started. Liquid in-glass thermometers are based on the principle of thermal expansion of substances when they are heated. A liquid in a glass tube, also called a capillary tube, expands when heated and contracts when cooled. A calibrated scale can then be used to read off the respective temperature that led to the corresponding thermal expansion. Such thermometers are also called capillary thermometers. The liquids used in such thermometers must have certain properties in order to be suitable for use. For example, they must not freeze at low temperatures, which is why water, for example, is not suitable. The liquid should also have a sufficiently high boiling point so that they do not vaporize at high temperatures. Furthermore, the liquid must expand evenly with the temperature in the measuring range used. Otherwise, an uneven division of the scale on the thermometer would be necessary. Also, for this reason, water is not suitable, since water expands unevenly due to the density anomaly. However, liquids which have all the required properties, and are therefore suitable for use in liquid in-glass thermometers, are also referred to as thermometric liquids. In the past, the highly toxic mercury was used, which has a solidification temperature of -39 degrees Celsius, and a boiling temperature of 357 degrees Celsius. Nowadays, usually blue or red-colored ethanol alcohol, with a melting point of -115 degrees Celsius, and a boiling point of 78 degrees Celsius, is used instead of mercury. In this temperature range, the everyday temperatures in the range between -20 degrees Celsius and +50 degrees Celsius can be well covered. The measuring sensitivity of liquid in-glass thermometers increases with the amount of liquid in the thermometer. The more liquid there is, the more liquid will expand and rise in the glass tube. For this reason, liquid thermometers have a reservoir to increase the amount of liquid in the thermometer. Too much liquid, however, would cause the thermometer to react very slow to temperature changes, as the heating of the liquid will take longer and the liquid will take longer to adapt to the outside temperatures to be displayed. Thus, the reservoir should not be too large, but also not too small. Why did people actually use toxic mercury as a thermometric liquid in the past? This was not only because of the wide temperature range of theoretically minus 39 degrees Celsius to 357 degrees Celsius that could be covered with it, but also because mercury hardly wets the glass tube. The capillarity is therefore lower and the temperature can be displayed and read off more accurately. Especially in the scientific field, this used to play an important role in keeping measurement uncertainties as low as possible when measuring temperature. We hope you enjoyed the video and found it helpful.
The next instrument is pressure thermometers. It is one of the most economical, versatile, and widely used devices in industrial temperature measurements. It is based on the principle of liquid expansion due to an increase in the pressure in a given volume of the temperature measuring system. So here's the video about pressure thermometers. Next slide po. Mercury in steel thermometer. This type of instrument has a linear scale and may be used for temperature ranging from negative 25 degrees Celsius to 550 degrees Celsius. The total expansion of mercury is dependent not only on the bulb temperature but also on the temperatures of capillary tube and Bourdon tube, which subjects the system to ambient temperature errors.
Behold, mercury thermometers. But where did they come from? Meet Daniel Gabriel Fahrenheit, born in Poland in 1686. Daniel was always fascinated by natural science. At 16, he began training as a merchant, but he still conducted independent research, especially with temperature. He traveled extensively and became a glassblower by 1717. Eventually, Daniel started manufacturing thermometers. Like any other scientist, Daniel knew his work depended on precision, and measuring temperature requires two things. First, a reliable way of indicating a change in temperature. Second, a scale against which to measure these changes. But here's the problem. Neither of these things existed in the 18th century. Sure, people had been making thermometers for centuries, but they weren't precise. Daniel knew this, and he created several new types of thermometers. His first devices used alcohol, but the most famous of his thermometers used mercury in a glass tube. When the temperature rises, the heat forces the mercury up through a narrow bore. This bore is usually filled with nitrogen, or left as a vacuum. Yet this wasn't his biggest stuff of genius. In 1724, Daniel proposed a scale for measuring temperature, setting 32 degrees as the temperature of ice melting in water and the temperature of the human body at 96 degrees. This system wasn't perfect, but after a few readjustments, it became the world's standard method for measuring temperature.
The next measurement is vapor pressure thermometer. It is a thermometer that uses a pressure gauge to measure the vapor pressure of a liquid. It is filled partly with liquid and partly with vapor of the same liquid so that there is a liquid-vapor interface in the bulb. This device follows one of Dalton's law of partial pressure, which states that if both liquid and vapor are present, there is only one saturation pressure corresponding to a given temperature. Here's a video about vapor pressure temperature.
In this video we will deal with the design and operation of a vapor in metal thermometer. So let's get started. The less popular vapor pressure thermometers operate on the same principle as liquid in metal thermometers or gas in metal thermometers. For this reason, they are also referred to as vapor in metal thermometers. In vapor pressure thermometers, a highly volatile liquid is used, but only partially occupies the thermometer volume. The liquid begins to vaporize and fills the rest of the volume with vapor. As a result, the pressure rises until an equilibrium between the liquid phase and the gas phase is reached. In simple terms, the rising pressure causes the vaporizing particles to be forced back into the liquid state. This equilibrium between vapor and liquid depends on the temperature. The figure shows the vapor pressure curve of water as an example. If the temperature rises, more liquid will vaporize and the vapor pressure will rise accordingly. This rising vapor pressure is indicated by a Bourdon tube, as with gas-filled thermometers. Conversely, a drop in temperature causes part of the gaseous vapor to condense and the vapor pressure to decrease. The indicated temperature decreases. Since vapor pressure curves are not linear, the scale of vapor pressure thermometers is not divided into equal steps. Due to the exponentially increasing vapor pressure curves, the scale distances increase with higher temperature, so that the measurement sensitivity and accuracy increases as a result. Vapor pressure thermometers should therefore be used in the upper third of the scale for sufficient measurement accuracy. Vapor pressure thermometers can be used at very low temperatures, which are only a few Kelvin above absolute zero. We hope you enjoy.
Next po, ang constant volume thermometer. This is used and insert gas, usually nitrogen, and follow the principle. The pressure of the gas increases with the increase in temperature at constant volume. It can operate with over a range of 130 to 540 degrees Celsius with linear range as large as 500 degrees Celsius. For karagdagang information po, ito po ang video.
So now we're going to see the gas thermometer working. So we're going to raise the gas, or raise warm water into the gas, and the gas will expand. Notice we've got the starting levels of the mercury with the two arrows there. Then as the warm water heats the gas will expand, which will force the mercury down on the right-hand side and up on the left-hand side. But this will also increase the pressure as well as the increase in volume. So when it reaches equilibrium and the two levels of mercury don't change anymore, then what we will do is come along, we'll grab the left-hand side of the tube and lift it, further increasing the height of the mercury, increasing the pressure, which will then force the mercury on the right-hand side to come back to the level that it started at. That's happening now. And when it gets to the level that it's starting at, we can see on the left-hand side the height difference of the mercury, and from that we can calculate the new pressure that the gas is under at the same volume.
Well, ito po pala yung slide kanina, hindi ko pala ata po na ito. Pasensya lang po. Next po, electrical resistance thermometer. Resistant thermometers have generally employed a metallic conductor in the form of a wire, which varies in electrical conductivity or resistance as its temperature varies. By exposing a wire to heat from a substance, the temperature of which is to be measured, and measuring the electrical resistance of the wire, the temperature of the substance can be determined. Next po ay ang metallic resistance thermometers or resistant temperature detector or RTDS. It is a temperature measuring device which is used to measure high accuracy 48 temperature. It determines the temperature by measuring the resistance of pure electrical wire. It relies on the linear increase in resistance of metal wire, usually platinum, with increase in temperature.
RTDs are thermoelectric sensors used to measure temperature. RTD itself stands for Resistance Temperature Detector, but they are also sometimes referred to as resistance thermometers. RTDs are generally more accurate and offer a greater stability over time than thermocouples and other temperature probes when monitoring within recommended ranges. It's known that the resistance of a metal changes with temperature fluctuation. RTDs take advantage of this principle by utilizing a resistive element. In practice, an external monitoring device, such as a data logger, will be used to apply a constant current to the RTD, and by measuring the resulting voltage drop across the resistor, the RTD's resistance can be calculated and correlated to a temperature reading with extreme accuracy based on the metal's resistive properties at certain temperatures. RTDs come in 2, 3, and 4-wire configurations. A 2-wire RTD does not account for lead wire resistance, which results in a marginal increase in the potential for error. Generally speaking, more wires equates to a higher accuracy. RTDs can also come with a variety of differing resistor elements, which will affect resistance, sensitivity, temperature range, and more. Therefore, it's best to ensure that the manufacturer's RTD specifications will suit your application's specific needs.
Next naman po ay ang thermowheel. They are tubular fittings used to protect temperature sensors installed in industrial processes. A thermowheel consists of a tube closed at one end and mounted in the process scheme. A temperature sensor such as a thermometer, thermocouple, or resistance temperature detector is inserted in the open end of the tube, which is usually in the open air outside the processing piping or vessel and any thermal insulation. For karagdagang info po, ito po ang video.
Monitoring require
Bale, yun pong dito po sa electric sensors, yun po yung present kaninang video. Bale, it consists essentially of two strips or wire made of different metals, conductors, and conjoined at one end, forming electrical conjunction at differing temperature. A thermocouple produces a temperature-dependent voltage as a result of the thermoelectric effect, and this voltage can be interpreted to measure temperature.
Next naman po ay ang semiconductor resistance sensor, also known as thermistor. It is an apparatus including a contact on a substrate, a dielectric material overlying the contact, a phase change element overlying the dielectric material on the substrate, and a heater element disposed in the dielectric material and coupled to the contact and the phase change element, wherein a portion of the dielectric material comprises a thermal conductivity less than silicon dioxide. Here's a video po for thermistor.
Thermistors have a few variations in design, but these two are fairly common, the flexible version and the more rugged fixed version. A thermistor is just a thermal resistor, meaning it's an electrical resistor which changes resistance with temperature. But there are two types of thermistors, the NTC or negative temperature coefficient and the PTC, the positive temperature coefficient. We saw earlier that the resistance of a metal typically increases as its temperature increases. And that was because the atom started to vibrate, which makes it harder for an electron to flow through the material without colliding. The PTC type thermistor behaves something like this. We call it positive because if we plotted the resistance with temperature, then we get an upward trend showing an increase in resistance with temperature. The other type is the NTC, or negative temperature coefficient. With this type, we use a semiconductor which behaves a little differently. As you might guess, we call it a negative temperature coefficient because when we plot the resistance of temperature, this type will actually decrease in resistance. This is to do with the structure of the atom of the material. If we look at a simplified atom of a metal, we have the nucleus at the center and then a number of electrons all on different orbital shells. A conductor has 1 to 3 electrons in its outermost or valence shell. Each shell holds a maximum number of electrons, and an electron has to have a certain amount of energy to be accepted into each shell. The electrons farthest away from the nucleus have the most energy. We need electrons to be able to move between other atoms in a material for it to carry electricity. Electrons are held in place by the nucleus, but if they can reach the conduction band, then they can break free and move. With a metal atom, the conduction band and the valence shell overlap, so it's very easy for an electron to become free and move. With an insulator, the outermost valence shell is packed. There's very little to no room for an electron to join. The nucleus has a tight grip on the electrons and the conduction band is far away, so the electrons can't reach this and escape. Therefore, electricity can't flow through this material. However, with a semiconductor, there's one too many electrons in the outer shell for it to be a conductor, so it will behave as an insulator. But as the conduction band is quite close, if we heated the material up, some electrons will gain enough energy to make the jump and break free from the atom. As more heat is added, more electrons move from more atoms, and so the material's resistance decreases. So its basic construction is just a piece of semiconductor between two conductors, and this is sealed with a protective coating. Okay, that's it for this video, but if you want to continue
Next po is quartz thermometer. The thermometer comprises a quartz resonator provided with electrodes disposed on the margins of the upper and lower main surfaces parallel to the length direction. The 50 electrodes are supplied with electric current so as to cause the resonator to vibrate torsionally. Next po. Pyrometer. The word pyrometer comes from the Greek word for fire or pyro and meter meaning to measure. It is a type of remote sensing thermometer used to measure the temperature of a surface. The pyrometer is ideal for taking accurate measurements of temperature without contact. Here's a video po for pyrometer.
The word pyrometer is derived from the Greek word pyro, meaning fire, and meter, meaning to measure. Back in the day, the original pyrometers were non-contacting optical devices which intercepted and evaluated the visible radiation emitted by glowing objects. Since then, the term pyrometer has evolved to mean a non-contact device which measures thermal infrared radiation emitted from an object to determine surface temperature. Simply put, the best example of a pyrometer today would be an infrared thermometer. So what does infrared have to do with temperature? All objects having a higher temperature than absolute zero emit infrared radiation. The higher the surface temperature is, the higher the frequency of that radiation. Infrared thermometers detect the infrared radiation frequency and convert that into a temperature reading. How does an infrared thermometer work? In its most basic form, an infrared thermometer consists of an optical system and a detector. The optical system consists of a lens that focuses the energy emitted from the target object onto the detector, which is sensitive to that radiation. The detector takes that focused radiation from the optical system and converts it into a temperature reading. For example, most IR thermometers use something called a thermopile. A thermopile converts the focused incoming radiation into an electrical signal using a series of tiny thermocouples. The signal is measured and displayed on the screen in the form of a temperature reading. The big advantage to using an infrared thermometer is that you don't have to come in direct contact with the object whose surface temperature you are measuring. However, there are some issues to using an IR thermometer that should be considered, especially in industrial applications, like emissivity. Highly polished metals typically have very low emissivity ratings, since they tend to be very reflective of ambient infrared energy and less effective at emitting their own electromagnetic waves. If you point an infrared thermometer with fixed emissivity at a stainless steel pot filled with boiling water, you might get a reading closer to 100 degrees Fahrenheit than 212 degrees Fahrenheit. That's because shiny metal is better at reflecting the ambient radiation of the room than it is at emitting its own infrared radiation. Some industrial infrared thermometers come with adjustable emissivity settings, so you can more accurately compensate for the type of surface being measured. Also, direct line of sight is required. An infrared thermometer cannot measure accurately through transparent objects such as clear plastic, clear liquids, and most types of glass. You can measure an accurate range of temperature through certain types of glass that fall within the wavelength spectral response range of the IR sensor. So if you aim at an object through a closed window, don't expect to get an accurate reading on that object. While IR thermometers offer a convenient way to measure an object's surface temperature, it is crucial to select the right type of device for your application to ensure accuracy in temperature readings. Still have questions? We have answers. Call or chat online with
Langmuir probe. It is a device used to determine the electron temperature, electron density, and electric potential of a plasma. Langmuir probe is one of the most common and widely used plasma diagnostics and measures parameters in the bulk of the plasma. Next po. Infrared sensors. An infrared sensor is a non-contacting electronic instrument which is used to sense certain characteristics of its surroundings by either emitting and or detecting infrared radiation. Next po. For additional information, here's the video.
A thermometer is a device that measures temperature or a temperature gradient. A thermometer has two important elements. One, a temperature sensor, in which some change occurs in a change in temperature, and two, some means of converting this change into a numerical value. The visible scale that is marked on a mercury in glass thermometer or the digital readout on an infrared model. Thermometers are widely used in technology and industry to monitor processes, in meteorology, in medicine, and in scientific research. There are many different types of thermometer available in today's market. Before you make your purchase, it is vital that you are made aware of the range of products available to you. You should also understand and consider each type of thermometer suitability for various different users. So today we will tell you all the different types of thermometer and their uses. You can find different methods of thermometer classification. We decided to go with the principle of operation as a defining characteristics. Therefore, there are 6 kinds of thermometer based on how they work. Here we will discuss one by one. First of all, liquid in glass thermometer. This type is the oldest and the most common kind of thermometer. It is used almost everywhere, and its principle of operation is very simple. This thermometer consists of a glass bulb and stem filled with a working liquid and an inert gas. When the temperature changes, the liquid expands or shrinks. When paired with a temperature scale, it is possible to use this occurrence to determine the temperature. Manometric thermometer. This type is also known as a pressure-filled or vapor pressure thermometer. It determines the temperature based on the change of pressure in gas or liquid. Manometric thermometer can be filled with gas such as nitrogen, condensation such as alcohol, chloromethane, diethyl, or mercury. Gas thermometer. A gas thermometer determines the temperature based on the difference in pressure or volume of gas it is filled with. There are constant pressure and constant volume gas thermometers. The latter is more commonly used. Gas thermometer can be filled with any gas, but the most popular option is hydrogen. This type works best with very low temperature. Bimetallic thermometer. This is a mechanic thermometer that works with a bimetal strip. Bimetal means that it is made of 2 metals. The strip is sensitive to the change in temperature and it causes mechanical displacement, which is used to determine the temperature. These thermometers are perfect for higher temperatures, as they become less sensitive and accurate at lower temperatures. They can be found in many household appliances like stoves, infrared thermometers. An infrared thermometer is a thermometer which infers temperature from a portion of the thermal radiation, sometimes called black body radiation emitted by the object being measured. They are sometimes called laser thermometers as a laser is used to help aim the thermometer, or non-contact thermometers or temperature guns to describe the device's ability to measure temperature from a distance. By knowing the amount of infrared energy emitted by the object and its emissivity, the object's temperature can often be determined within a certain range of its actual temperature. Infrared temperatures are a subject of devices known as thermal radiation thermometers. Digital thermometer. Digital or electronic thermometers are one of the most recent developments in the thermometer field. Instead of using liquids or gases paired with a temperature scale, they have a digital screen, which can show you the readings in a mere seconds. A digital thermometer has a thermometer that reacts to the change in temperature and projects the result on the thermometer screen. Clinical thermometer. A medical thermometer, also called clinical thermometer, is used for measuring human or animal body temperature. There are 3 most common clinical thermometers used in hospitals and homes. Mercury-filled thermometers. One of the oldest types. Mercury-filled thermometers are slowly disappearing from most countries. In addition to not being the most accurate, they might be very dangerous if broken. The mercury inside is toxic to people and the environment. Alcohol-filled thermometers. A safer alternative to the previous type. These thermometers use color alcohol that expands when exposed to increased temperature. However, both of these liquid-filled thermometers require some time to show the temperature. If you want immediate results, consider one of the following options. Digital thermometers. Digital thermometers are quickly replacing all of the old liquid in glass versions. They are fast, accurate, and convenient. With the help of oral, rectal, and armpit digital thermometers, you can get your results in mere moments. Dear sir, thanks for watching the video. For more update, please subscribe to our
And that concludes our presentation. Quiz na po ang sunod.
Okay. Thumbs up po para sa mga nag-present parang it ngayong midterms, engineers. Lalo po sa last group, ano. So, by the way, magsagot po ng quiz and I will wait it until 8 p.m. Okay po. Engineers. And then next meeting po is exercise. Ano po? Okay. Goodbye. And God bless.
Thank you po, sir.
Thank you po.
Thank you po.
Sir.
Thank you po.
Thank you po.
Thank you po.